alaikum. My name is Rabia, and we today will just simulate some cases of mechanical vibration in Simulink, and we will see the graphs of it. The case here we have 500 cosine WT. We need to start to make this setup, and our question is this: it will end to 1 over m multiplied by fx, I think. Let's see just the equation. We need to ft, not fx. Yes, ft minus kx. This is our equation. We convert to this because this is the ft. Okay, we need to put this in the simulator. Now let's start our setup. First, we need the source, which is the sine wave. Then we can convert it to cosine wave. Yes, this sine wave. Then we need some function. Yes, this. Okay. Plus gain integrator also scope. And now just make things bigger to just more focus and to see the numbers. So here, okay, we need two integrators. This first one, this second one, just copy paste. Okay, two gains, one here for the mass and one here for the k coefficient. Just make it like this. And here, as you see, one is negative, one is positive. So, one negative, one is positive. What is ft? We have 500 cosine. So the phase will be pi over 2. Then link things together. Flip this. Link it here. And here. Here for the mass is 1 over m, so 1 over 100. Here for the k coefficient, which is 40,000, apply it. And now we have 4 or 6 conditions. One is 0.1, 0.5, 0.95. Okay, which is will be 2, and here will be 10, 90, 20, 21, and here is 60. Now let's start the first, which is 2. Let's see what happened, or which graph we have. Yes, this graph Uh, you can see this concave is not what's mean not uniform. Let's go to 10. Run. See. Just down, up, down, up, down, up, and it's infinity because there is no damping here. Okay, 19. This is 19. It's bigger. And if you see or notice, when omega is less than omega n, the system oscillates, but not too much. Now, if omega equal omega n, what happened? It's increased significantly, which is the resonance. Now, let's go 21. Look, the same as, or approximately the same as 19. And now let's go to 60. As we said, for omega more than omega n, the resistance will respond, but the amplitude decreases. Yes, see the distance between the waves is so small. The waves is more. The displacement is strongly influenced by how close the forcing frequency is to the natural frequency. And for the resonance omega equal omega n, the system vibrates with the largest amplitude, especially since it's undamped. Away from resonance, the system reacts less intensely to the same forcing amplitude. Let's go to the case 2. Now for the second case. This is our second case here. So you see we have here damping. So we need to add another gain for damping. Here say we need the same as A, which is this frequencies, and with conditions of damping. The same equation, the same mass, the same K. So we need just add damping. As we said, this is 2, then 90, 20, 21 here, and here is 60. Okay, now we want to start to make it. Just we need another gain. We choose it this, copy paste and add it like this. We need to add another minus sign here and make, okay, just arrange it and change the value to 1000, which is the first condition. Or will be ft minus cx naught minus kx. So now 2 minus, this is positive. And now let's start the scope to see the graph. So you can see this is not stable or not uniform. Then start to be uniform here. You make it bigger, yes. Okay. Now let's change it to the same thing, but the wave is just the distance. Okay, from 2 to 10, let's see the difference. More waves, and the distance is between them is short or small. 19 and start. More waves, and again is closer to each other. 20. There is no big difference in 20 between 20 and 90. Just the waves is bigger and more stable because 20 is at the resonance, which is omega equal omega n equal 20 in our case. And 21, let's to run it. More and more waves, but you will see the difference if you go to bigger number, which is 60, and run it. Then you will see the difference. This is in case of 20. Of 60, you can see the waves is start to go up, down, then up, down. Then will be more stable and more uniform. Now let's go to another condition, which is 2000, and start from 2. Apply and OK. 1. If you see, here is more uniform than the before. Let's see 10 and 1. And here is more uniform than before, and you can see this approximately the same, the peaks. Okay, 19 and run. Let's see. More waves, more close together, and it's more stable for the system. 20 should be more stable because it's at resonance, which is omega equal omega n. Yes, approximately at the same magnitude. And now let's go to the bigger number, which is 60. And this is our case. Up, down, and more stable than 2000 and 1000, I mean. Let's go to 4000 and frequency from 2. 4000 here. And also I forgot to change this to C, which is damping. And start. Then let's see. More and more the waves are more organized, and let's see then run and see. This is more stable than before, than the 2000s. You can see the peaks is the same, but just started here. Let's see 19. Waves is more closer together. Let's see 20. And 20 should be no more oscillations or no more vibrations. Yes, it's more stable. The waves is closer together and more waves. Even we go up and up, there is more waves will create, not 90, 60. More frequency, more waves. And you can notice it more stable than 2000. What if we go to 3000? And 2 here. Let's see what will happen if we run more organized. The waves, you can see the starter here. Go to 10 and see. And you can notice again, here is more stable than before. And 1 second. Okay. Now we need to test 10 or 90. We finished 90. Yes. We need to see the waves is more organized here because the system is when we get close to the resonance, it's be more stable. In our case, as we say, the resonance is 20, or omega will equal omega n at 20. And run. Let's see. Yes, it's more stable. Just start here like this, then it's just the system uh, return to the stable case. C to 860 and run. Let's see. You can notice again it's more stable than 4000. So what happened here? Resonance effect is reduced. When omega equal omega n, the peak displacement will be much lower than in part A, which is our first case. And the response settles faster and is smoother at high frequencies. Also, the damping helps reduce vibration fluid. No infinite oscillations as before. In the undamped case, oscillations continued forever, but here energy is dissipated by damping. And now let's go to the last case we have. And for the last case, we have here the third case. He said the equation will be 0.1 sine, and it's yt, and we have here xt. So there is a little different in our setup. So the first we need another gain, which is k, and flip it, put it here, and we need another gain of the dam, also flip it, and we need derivative, yes, we need this, and we need to add another plus sign here, yes, just we want to move this here, and this will be here, like this. And we need to add or edit this sign to 1.1, and this will be 0. And then everything is the same, I think. Yes, the mass is the same, k is the same, we say the same as A, the same as B, and explain. Okay. Now, let's see the graphs, then we will talk about it, or we will talk about the observation of this Simulink. So the first one, 1000, and frequency, this our first one. You see some lines not organized. Okay, let's say if we raise it to 10, yes, it's the same thing. I think here is stable and just a little bit raised here. Let's go to not here, sine wave 19, and run. It's more, the distance between them is a little, and waves is more waves and peaks. Let's go to the resonance, like this, 20, and run. As you see, yes, more stable at the resonance, a little of oscillation or no oscillation at 60. Okay, it's big peaks here, then a little down, then down, a little up, then organized here, or the system being stable at that point. Okay, change the damping values to 2000. Let's see, and run. Look, even we go to 8000 or 4000, it will be more organized, it's more stable. So go to 10. More organized than before. And let's go to 19. Yes, as we see, this is a little bit, then it organized at the same values up and down. Let's go to 20. It's more stable, more waves. The distance between the waves is a little smaller than 19. 21. It's a little difference between 21 and 20. Now 60. And this we can see or notice the difference. Yes, this up here, but it's more stable than 1000. Let's go to 2 here, 4000, and here 4000, and 1. The distance here is bigger than before, and this line is more organized. The peaks are the same. When we go to 10, is it stable or not? It's more stable than before. Let's go to 19. And it also better than before. The waves is more, as we said, and the distance between them, even we go more up and up, it will be this more waves or more peaks, and the distance between them is a little bit smaller. Let's see the 21. Okay, it's a little different between the 1 and 20, a little, but when we go to 60, because the difference between the numbers is bigger. Yes, and you can notice the start of the waves is more organized than before. Let's go to 8000, and here 8000, and let's see. I think 60, 0.1, yes, here too. It's more perfect than before. Look at the waves. You can see the stable system disappear. When we go to 10, this is the same or different between 8000 and 4000. Yes, it's a little the same peaks 0.1, approximately all but 0.1 and all 0 minus 0.1. Let's go to 19. Also approximately all the same. So you can see the system is stable. Or there is no oscillation here. And for 20 also, it's no oscillation. Approximately no oscillation. And now see at 8060 frequency. Look at the starter of the system. Just dot a little bit, then it's be the same magnitude 0.8 or more than 0.08, just a little bit. You can see the peaks are approximately the same. So, as the damping coefficient increases, the system's displacement in response to the harmonic force decreases, especially near resonance. The sharp peak observed in lightly damped systems becomes flatter with higher damping. This indicates reduced displacement transmissibility, meaning the system is better at suppressing vibrational motion transmitted from the external force. So, at low damping, high resonance peak around uh, Wn equal 20, which is the frequency. The system reacts sharply when excited near natural frequency. At C degrees, resonance is flattened, amplitude become lower. The system becomes less responsive to the same force, and at high damping, which is 8000, the system is heavily damped, response is smooth and slow, no sharp peaks. Max amplitude is the smallest. And here we reach the finish or the end of the video. Thank you for watching and see you later.